Everyone, my name is Divyansh, and I'm pleased to present our paper on corrupting neuron explanation of deep visual features. So DNNs have become a powerful tool for solving complex machine learning problems. It has found its use in different applications, including self-driving, playing computer games, healthcare, and chatbots. DNNs have shown promise for use in safety-critical applications. However, their black box behavior makes it difficult to place trust in their predictions in high-stake settings. Interpretability methods aim to increase trust in DNN's prediction by providing an insight into their internal working. Interpretability methods can be broadly categorized into two classes, instance level methods and global level methods. Recent work has shown that interpretations provided by instance level methods can be easily manipulated. However, the robustness of global interpretability methods has not been studied. In this work, we are going to focus on studying the robustness of neuron explanation methods, which form a subclass of global interpretability methods. NEMs provide explanations for each neuron by looking at the activation pattern of images in the probing dataset. Some typical examples of NEMs include network dissection and Milan. NEMs have been used to explain DNNs in medical tasks, including brain tumor segmentation. Their use in critical applications makes it important to understand NEMs vulnerabilities and caution the community against blindly trusting explanation from them. This slides present a unified pipeline for NEMs. Input to NEMs is a trained DNN model and a probing dataset. For each image in the probing dataset, we compute the region with activation above the threshold and then use a similarity function that outputs a concept based on an activation pattern. NIMs require probing dataset, which is domain specific and generally collected by end users working with DNNs. This makes it vulnerable to noises and adversaries who can corrupt the probing dataset to manipulate concepts and fool stakeholders into trusting a model. The goal of this work is to understand the robustness of NEMs against different kinds of perturbations. We will first analyze the robustness against random noise and then against a novel perturbation algorithm that can modify neuron explanations with a high success rate. So let's start with the random perturbation. Here we add a Gaussian random noise to the images in the probing dataset. Figure on the left shows the percentage of manipulated neurons explanation in the layers of VGG16. And we find that even adding a small random noise with a standard deviation of 0.02 can already change the assigned concepts of up to 28% neurons in the deeper layer. The overall pipeline for generating crafted perturbation can be divided into three steps. In the first step, we compute act average for a concept. The idea here is to summarize the activation of a neuron for a concept by a scalar quantity act average. The next step is to compute the perturbation for the image. Here we solve the following objective function with the projected gradient descent. And finally, we add the perturbation computed in the last step to images in the probing data set, and the new concept assigned to the neuron changes to the target concept bed. This slide shows qualitative results for crafted perturbation against network dissection to change the neuron's concept from bus to bed. We observe that the concept gradually changes from bus to bed as intensity of attack increases. This slide demonstrates the effectiveness of our perturbation algorithm. The figure on the left shows the percentage of units modified for network dissection. We are able to reach 98% success rate with an epsilon 3 by 255 in the higher layers. The figure on the right shows the result of crafted perturbation on Milan with description compared using F1 word score. We see that the word score decreases to 0.4 in the higher layers. This concludes our presentation for our work. In summary, we have demonstrated that the NEMs are not robust to perturbations. They are vulnerable to corruption of probing dataset, which questions their trustworthiness in safety critical applications. Further, we designed a novel perturbation algorithm that can manipulate any NEM with a high success rate. Thank you.